Hello all. We shall discuss about a very important experiment in electrical engineering, and the experiment is uh, basically about the three-phase connection. About the three-phase connection of load. Okay. So the title of the experiment is determination of phase and line quantities in three-phase star and delta connected loads. So the fundamental theories required in order to understand the three-phase and its importance, followed by different notations, the experimental conduction circuit procedures, experimental setup, along with the verification of theoretical and practical aspects. So we shall discuss each of these one by one. To begin with, first of all, we shall discuss about what is the importance of three-phase, right? So as we can see here, these are the representations for generators. So this is again a representation for a generator. This is a representation for actual transmission tower, electrical power transmission tower, and this is the transformer, right? Now, all the equipments I have listed here, these all are three-phase in nature. Now, what is the importance of this three-phase is, first of all, whenever we have three-phase system, as it is given over here, so whenever we have three-phase systems, first advantage is that the power to weight ratio, no, it is better. So what is the meaning of power to weight ratio is, in order to do a same amount of work, the actual capacity of the machine in terms of its weight is reduced if we opt for three-phase. So whenever we have three-phase system, the actual weight of the machine is reduced. That is one point. Another thing is, whenever the power is transmitted through three-phase, then actual power losses in the conductor are less and the requirement of the conductor material is less. Okay, so this is the another reason. Apart from power to weight ratio, even the amount of conductor material required and the actual power loss in the transmission line is less if it is three-phase. Apart from this, there is another important application of the three-phase power supply. That is, you take any of the industries. Okay, just to give more practical insight, I have just given some of the examples like steel industries here and a textile industry over here, right? So any industry you take, practically it consists of a motor arrangement like this. Practically any industry consists of a motor arrangement like this. And all the electrical motors, they are made up of three-phase. So why they are made up of three-phase is, as already it is evident for us that the power to weight ratio, it is high. Mean to say that the motor can do same amount of job as that of our single phase machine, but weight will be reduced with reduced weight. Okay, with reduced weight. So because of this reason, as it is evident here, the generators are of three-phase nature, transmission line, transmission tower, three-phase, and again the transformers involved, they are also three-phase. Added advantage is that the load, whatever they have to supply, all of them are three phase. So here just again another type of three phase load, which is given over here is a three phase lamp load, right? So total advantage of three phase system is whenever we have three phase system, the efficiency is also increased. Okay, efficiency gets increased and the losses in the line gets decreased, and the same amount of work can be done with more efficient with a machine which is actually less denser, right? That is nothing but the power to weight ratio is good, right? So these are the advantages for going for a three phase system. And practically, okay, apart from residential use, all the other applications involve three phase AC only. All the other applications involve three phase AC only. Now, if this is the case, then what is this three phase? Right, so we have to first try to understand the meaning for three phase. So whenever we have three phase, as you can see in the waveform given over here, we'll have three sinusoidal waveforms like this. So you can see that this is one sinusoidal waveform. But in the case of three phase, there are three sinusoidal waveforms like this exist, right? So in the case of three phase, there will be three sinusoidal waveforms like this. Now, what is the advantage, or anyhow already we have discussed, but the process I'll just highlight here. See in the diagram, whenever you see that this either the north pole and the south pole arrangement, right? So whenever it coincides with this red arrangement, we can see that the power will be, the voltage developed will be maximum. So at this instant, we can easily identify that the coincidence between north and south pole is maximum. Similarly, whenever if I take the example for, let us say that this one, right? So for this also, whenever it continuously rotates, we can say that the power will be maximum whenever this north pole and south pole is exactly in alignment with the conductors. So that's what we can just mark the maximum voltage which can develop. So similarly, we can also mark the maximum voltage for another phase, that is which is given over here by green, right? So we'll have, see how many minimum and maximum positions we have, right? So since it is alternating circuit, we'll have actually in the case of three phase, we can find out that we have 3 plus 3, that is 6, 3 plus 3, that is we have 6 positions. So 6 positions, or else you can just say that to just indicates that the maximum values, right? So this is the advantage, because if we have only one phase, then you can see that only one maximum here and one maximum here we will get. But in the case of three phase, the advantage is that since we have three waves like this as given in the diagram, so obviously the amount or the effort put in by the generator in order to do the useful job is actually more, right? So that you have to understand that whenever it is three phase, the meaning is that we have three waveforms as given over here, right? Now let us look into the circuit aspects and along with the aim of the experiment. So the aim of this experiment is to determine line voltages, phase voltages, and line currents and phase currents in three phase star and delta connected loads. Okay, so we shall begin with the discussion of each and every term involved in the title of the experiment. That is what is the meaning for line and phase, and what is the meaning for star and delta, right? So we shall understand the title itself by the way of explanation for each of the terms involved. Okay, so mainly we have to just understand that we are measuring voltage and current. Okay, we are measuring voltage and current in a three-phase load. Okay, but the load is connected in two fashion. One is called as star, another one is called as delta. Right. So what is star and delta? We shall discuss in detail. So the aim of the experiment is, as the title itself is new to us, first of all, we shall try to identify the type of connection, and we shall also try to know the different notations associated with three-phase AC, that is the line and phase, and we shall determine the relationship between the line and phase quantities, that is through the experiment. And once we are done with the experiment, we shall also establish if there is whether there is any link between the theoretical calculations and the actual practical results for star and delta connected load. So this is the fourth objective. Now, many a times we say that star and delta. So what is this stands for? Okay, so in order to understand this, let us take a very simple example. So we know that this is a simple resistor. Now, whenever we consider any resistor like this, we know that it consists of two terminals. Okay, it consists of two terminals. Now, first terminal, I'll just call it as ES, mean to say that the starting point, E for end. So remember here that ES stands for starting point, E stands for end point. Okay. Now, in the case of three-phase, as we have seen that the generator involves three voltages, three-phase voltages, right? So there will be three waveforms. So obviously, the load, whatever we connect, should also be of three-phase nature. So whenever it is a three-phase nature, we don't have only one resistor, but we have three resistors. We have three resistors like this. Okay. And to each of the resistor, I can just mark the starting point, end point, starting point, end point. Okay. Now, whenever the three-phase concept comes into picture, it is actually identified by RYB, whereas R stands for red, which is the color used to identify first phase. Y stands for yellow, so yellow is the color to identify the second phase, and B, so B is the blue, so which is the another color to identify the third phase. So this is for first phase, so this is for second phase, and this is for third phase. Okay, so in our country we generally use RYB, but some other countries they also use RYG, that is green. Okay, so that is just a color code indication, right? Now we got to know that whenever we have three-phase source, it is nothing but what? RYB. Now we shall just adopt that in the diagram whatever we have already drawn. So let us call this resistor belongs to R phase, this resistor belongs to Y phase, and this resistor belongs to B phase, right? So that the terminal associated with R, I can write it as RS, terminal associated with the end point associated with will be RE, and this is YS, YE. This is BS, BE. So please pay attention here how we have written down the notations is R suffix S and R suffix E, Y suffix S, Y, E. Then B, S, comma, B, E. Okay, so this is the way to write down the terminals. Okay. Now we know that whenever we have only one register like this, then if I say that the starting point, end point, right? So how many number of terminals we have here? So we have total two terminals here. One is the starting terminal, another one is end terminal. But in the case of three phase, as we know that we have three registers. We have three registers as given over here. We have three registers as given over here. For these three registers, anyhow, we have marked the terminals as given over here. So we have anyhow marked the terminals. So if you count this number of terminals, there will be total 6 terminals. 1, 2, 3, 4, 5, and 6. Right. Now I will explain you the meaning of star and delta connection. But the basic whatever I have explained, that you should be able to remember, right? Because we got to know that now there are actually in a three-phase load there will be 6 terminals. Okay, there will be 6 terminals. Now, what is the meaning of the star or delta is how we are connecting these 6 terminals. How we connect 6 terminals. Okay, the manner, the fashion we connect these 6 terminals, right? That will give you idea that whether it is star connection or delta connection. Remember that only the connection of these 6 terminals will define that whether it is a star connection or delta connection. Okay. Now, what is the star and delta? We shall now discuss. So, in the case of star connection, all the endpoints are connected. Now, anyhow, we know that how the resistance are represented, right? So, let us say that this is RS, this is YS, this is BS, and this is RE, this is YE, this is BE. So in the case of star connection, we just connect endpoints. We just connect endpoints. Okay. So whenever we connect endpoints and to the starting points, power supply is applied. Okay. To the starting points, power supply is applied. And endpoints, they are just, so we apply electrical power supply here to the starting points, and the end points, they are connected together. It is called a star connection. Now, what is exactly I am explaining here is, see, this is RS, this is RE, this is YES, this is YE, and this terminal BES and BE. So you see that in the case of star connection, all these endpoints, they are shorted, they are connected together. Okay, so this is called a star connection. See here, RS, so RE, YE, BE. They are connected together, and RS, YS, BS, they are used for the purpose of applying the power supply. Now we shall discuss about the delta connection. Okay, so in the case of delta connection, it just looks like Greek letter delta. Looks like a Greek letter delta, hence it is called as delta connection. So in the case of delta connection, you have to remember one simple rule, that is end to end. Okay, that is end to end connection. So what is that end to end connection? I will explain you. So before that, please remember that in the case of star connection, what we have done is all end terminals are connected. All end terminals are connected. Now, in the case of delta connection, there is some difference. Okay. So, in order to understand that, I will just draw the three registers once again, along with their notations. So, we know that this is RS, RE, YS, YE, BS, BE. So in the case of delta connection, it is called as end-to-end connection. So the meaning for end-to-end is this end is connected to starting of next phase, and end of Y phase is connected to the starting of next phase. Okay. Similarly, the end of last phase and the starting of first phase, they are connected together. Okay, this is called as delta connection. So once again, I will draw and explain this. So in the case of delta, as we can see here is, in the case of delta connection, end of one phase is connected to starting of next phase, end of Y phase is connected to starting of next phase, and end of B phase is connected to starting of next phase. So how to identify this here is here. If this is RS, RE, then this is YES, and this is YE. Similarly, this is BS, this terminal is BE. Okay, so remember that BE and RS, they are connected to it. BE and RS, they are connected to it, like that. And similarly, RE and YS, they are connected together, and BS and YE, they are connected together. That is the junction point for this nodes, that is RSBE. You can see here, this is the junction point for RSBE connection. Then REYS, this is the junction point. Then YEBS, this is the junction point. Okay, so this is what is called as the delta connection. Okay, it is end to end connection, that is end of one is connected to starting of next phase, right? And end of that particular phase is connected to starting of next phase, like that. Okay, this is what we have to remember as star and delta connection arrangement. Now with this as the basis, we shall now discuss about the apparatus required to conduct this experiment. So to conduct this experiment, we require one three-phase auto transformer and one three-phase resistive load. Okay, so this three-phase resistive load is of 400 volts, 10 amperes. is 400 volts, 10 amperes, and we also require ammeter of range 10 ampere and voltmeters of 600 volts and 300 volts. So as already I have explained you the star connection of load, I shall just mark the terminals so that we can easily identify the terminals. So this is RS, RE, so this is YES, YE, BES, and BE terminal of the load. So what does the circuit says is a three-phase supply is applied. You can see that this R phase, Y phase, B phase. So power is applied from R phase to ammeter, then ammeter to RS terminal available at the load. Similarly, from Y to YS terminal available at the load, and the B terminal of auto transformer is connected to the PS terminal of the load. Okay, so this is the connection for star type of load, right? Overall arrangement. Now we have to first understand very important terminologies related with three phase. That is the meaning for line and phase. Okay, so this line and phase is associated with both voltage and current. Similarly, this line is also associated with both voltage and current. Now, if we look at the circuit diagram, we can easily mark that there is notation for IL equal to I phase and VL and V phase, VPH. So what are these? Okay. So first of all, for the star connection, we shall try to know what is phase voltage and what is line voltage. Okay. So for star connection, we know that we have connected our resistors like this. So whenever we have connected resistors like this point is called as neutral. Okay. So in the circuit diagram also, we can mark this point. Okay. So this point is called as neutral. So if I measure voltage between one line and neutral, if I measure voltage between one line and neutral, it is called as phase voltage. So you see here what measurements we are taking. This particular case is we are measuring between R phase and the neutral, right? So this voltmeter is connected between R phase and neutral. So what does the phase voltage stands for? It is whenever we measure voltage between one line and neutral. So it is called as phase voltage. Similarly, what is called as line voltage is whenever we measure any voltage. So whenever we measure any voltage between two lines, it is called as line voltage. So those two lines are nothing but you can see between R phase and between Y phase. So we are now measuring between two of the phases, right? So this is called as line, right? So line phase is nothing but between two lines, that is R and Y, or R and B, or Y and B. If we measure, then it is called as line voltage. So this is how to understand that the phase voltage means between a neutral point and any one line. So whereas line voltage is between two lines, right? So this is the definition for line voltage and phase voltage for star connection. Now, we shall also try to know what is the meaning for this phase current. So in the case of star connection, this line current is equal to the phase current. Okay, line current will be equal to phase current. So what exactly we have to determine is, in the star connection, we have to prove that line current is equal to phase current and line voltage is equal to root 3 times of phase voltage. So anyhow, I have explained you the meaning of line voltage and phase voltage, and we have to finally calculate the power. So main calculation or main theoretical idea for this experiment is, we have to prove that line voltage is equal to, sorry, line current is equal to phase current, and we also have to prove that line voltage is equal to root 3 times of phase voltage. Okay, so this is for star connection. Now for delta connection, so once experiment setup is ready as per the given circuit diagram, we have to note down the readings, that is practical values. So what will be these practical values? And here also we have to note down the practical values, and we have to calculate these things, which I shall just explain at the end of this video. And we have to note down these things, right? So whatever is given over in the tabular column is theoretical. So this we have to calculate by the formula. So we have to calculate using formula. So in the tabular column, wherever it is mentioned that it is theoretical value, we have to calculate them using the formulas discussed, right? So this is the delta connection. As already I have explained, for delta connection also, if you just look at the circuit, okay, up to here it is same. The circuit is same as that of our star connection. The change will be only with respect to the way we have connected the load. The way we have connected the load, there will be change. Otherwise, the circuit connection is same. So we shall now, and I have explained you the way delta connection is done. So in order to do the delta connection, you know that end-to-end connection. That is, if this is RS, RE, YS, YE, BS, BE. Right. So this end is connected to the starting, this end is connected to the starting, right? So only the changes, since we have to measure the current, what we have is, in between this RS and B, we have the ammeter. So let us look at the circuit actual connection. So this is RYB, the output terminal of the auto transformer. So see here. So this, I'll just mark this terminal as RS, this terminal as BE. So this is, if this is RS, then this will be RE, and this will be YS, this will be YE, and this will be BS. Okay, so these are the notations, terminal notations available at the delta connection load. Okay, so for delta connection load, we have to concentrate about the line current and phase current. Okay, so please remember that whenever we have IL or IPH, then IPH stands for phase current and IL stands for line current. Similarly, even for delta connection or star connection, if I write as VL, mean to say that it is line voltage, and if I write down as VPH, mean to say that it is phase voltage. It is phase voltage, right? So that is how we have to read these things. Now, once we are we have these different notations available, right? So how to conduct the experiment, that we shall discuss. But before that, no, we shall try to know this line and phase current as applicable to the delta connection. Okay, for delta connection, as we can see that this is the line current. So whenever this line current enters here, it gets divided into two currents. It gets divided into two currents, and the currents within this delta connection, within this mesh, are called as phase currents. The currents within the mesh are called as the phase currents. And remember that this line current is always greater than the phase current. That is, it is root 3 times of phase current. And the interpretation we can just have by looking at the circuit. So whenever this current flows up to this point, right? So because there is a junction here, the current gets divided into two components. Mean to say that any line current, let us say that IA, okay, any line current, let us say that IA comprises of two phase currents. Two phase currents, because we know here that it just gets divided into two components. Similarly, it can be applicable for the remaining line currents also. So with this as the basis, if we look at the formulas, the mathematical calculations for delta connection, line voltage will be equal to phase voltage, whereas the line current is root 3 times of phase current. So that anyhow we have seen in the diagram, that is, whenever this current enters here at this junction, the current gets divided into two parts. Similarly, at this junction, the current divides into two parts, and at this junction, the current gets divided into two parts. Okay. So the current which is within the mesh, the current flowing within the mesh is called as the phase current, right? And that current, which enters the node is nothing but the line current, and the line current comprises of two phase currents. So only the thing what we have to remember is whenever we say that line, either it is voltage or current, okay, it involves two quantities. That's what you have to always remember. So because in the case of phase, in the case of line voltage also, it is between this line and this line. Similarly, in the case of line current, we are actually interested about the current, which gets divided into two components. That is, this one, the current flowing in this path, and the current which flows in this path, right? So it actually determines the line current over here. Okay, that's what is the main interpretation. So we have to follow these mathematical steps, and we have to note down the readings during the conduction of the experiment. So again, here we have to note down that wherever practical is there, we have to note down the readings, right? And wherever, so this VL is there, we have to note down, and this is what we have to calculate. So wherever theoretical is there, we have to actually calculate. So this and this, okay, we have to calculate, and we have to prove that the theoretical calculation is equal to the practical calculation. So whatever we calculate theoretically must match the values available practically. Okay, that is what we have to verify. So this verification, we shall now have this verification by way of conducting the experiment.
Now I will introduce you to the different equipments and the experimental setup, materials required to conduct the experiment of three-phase star and delta connection. To begin with, whatever you people are seeing here, this is the power supply board, and in this board you can see that this is called as triple pole single throw switch, and whenever three-phase power supply is there, you can identify that it is always given with red, yellow, blue. So red, yellow, blue, these indicates that these are the three-phase power supply. That is, R is one phase, Y is the another phase, and B is the another phase. Along with that, black terminal is the our neutral part. So please remember, whenever three-phase comes into picture, we have some arrangement called as a triple pole single throw switch along with the RYB supply. Next, we shall now look into the another important equipment required for our connection, which is a auto transformer. So this is a three-phase auto transformer. So as you can see, these terminals are the input terminals of the auto transformer, so that the power supply from the switchboard, which I have already shown, is taken. So we have connected the power supply from switchboard to the auto transformer input. Okay, and you can see that each auto transformer, it is also called as dimmer stat, and it is nothing but the variable auto transformer. That is, voltage can be varied as it is given here, and these three are the output terminals of the auto transformer. Okay, so from these three terminals we can connect our load. Okay, so these terminals are useful to connect the load. Now, very important feature of this auto transformer, as you can see, is there is a rotating switch or knob is provided, so that you can see that by handling this we can rotate. Okay, and whenever we rotate, we can apply the required voltage. Okay, let us say that if we want to apply 10% of the rated voltage. So if I take three phases 400 volts, then 10% of 400 is 40 volts. So if I want to apply 40 volts, then from 0 to 10% I have to move. Okay, so it is useful to apply the required amount of voltage, because there is a provision provided. You can see that there is a knob provided and there is a provision provided, so that we can actually set the voltage in the range of 0 to 100%. Now, apart from this, another very important experimental equipment required is a three-phase load. Okay, this is a three-phase load. So whenever three-phase load we say, you need to identify that there are again terminals are there, like red, yellow, blue. Okay, so whenever we have this red, yellow, blue terminals, you have to again understand that for each phase there will be one load. So you can see that R, S, R, E, that is, this is R phase, this is Y phase, and this is B phase. So whenever we have to apply the load, you can see that there is a rotating switch. Okay, you see that now this mark indicates that it is in off condition. So whenever I turn on, so whenever I rotate the switch, now the load is on and I can just turn it off. So I can also turn it on in the left direction. So you can see that there is two positions for on and two positions for off. That is, at this position, if I can just turn it down, this is off. Okay. Similarly, at this position, if I turn it again upwards, it is off condition. Okay, so that we can just turn on the load, we can turn off the load. Like that, as per the requirement of the experiment, we can have, we have here 10 rotating switches. Now, the quantities whatever are required for this particular experiment, that is the voltage and current, they are actually measured by using a voltmeter and ammeter. So you can see that these two are the voltmeters required for the experimental setup, and these two are the ammeters required. Okay, so whenever we perform star connection, we require we require 2 voltmeters and 1 ammeter whenever we perform star connection. So please you have to remember that whenever we perform star connection, we require 2 voltmeters and 1 ammeter. But whenever we perform delta connection, please remember that we should require 2 ammeters and 1 voltmeter. Okay, this is very important. Only there are 4 4 different measuring equipments are there, but at a given point of time we may require 2 ammeters and 1 voltmeter for delta connection and 2 voltmeters and 1 ammeter for star connection. Okay, so this is very important point you have to remember before we actually conduct the experiment. Now we shall conduct the experiment, that is the calculation of line parameters for star and delta connection. Okay, and here I have already explained the different equipments required. Now the circuit is ready for conduction. So before we actually trace out the circuit, I will explain you the different meters involved once again. See here, whenever we have a voltmeter, if you see the circuit diagram, so one of the voltmeter, where we have to measure the line voltage, it is connected for a range of 0 to 600. Now see here, for this voltmeter, one terminal is the common connection and other one is the 600. That is what is the connection is involved. Now if you see the connection of another voltmeter, which is VPH, that is the V phase voltage. So for phase voltage, whenever we have done the connection, please see that our specification stands for 0 to 300 volts. So common connection and 300 volts. Okay, this is very important to understand. Okay, now we shall trace out the circuit. So whenever we trace out the circuit, we shall first follow this circuit diagram. And in this circuit diagram, always first we have to trace out the series connections first, followed by the parallel connections. Okay, so whenever you do any of the series connections, you have to ensure that you have to use thick wires like this. Okay, you have to always use thick wires like this whenever you are doing any kind of series connection. So the meaning of series connection is nothing but, if you see in this circuit diagram, any continuous connection, so from R it has started, any continuous connection where ammeter is involved or not involved, okay, is any direct connection is called as a series connection. You can see here from R to ammeter to RS, then Y to YS, B to BS, these all are called as series connection. Okay, so I'll just come from this particular point and I will just show you where this is located in our experimental setup here. So this is the TPST switch, and you can see that this is exactly has been shown in the circuit diagram along with its 3 poles. Okay, so RYB and a TPST switch. This is nothing but, in this circuit diagram you can see that RYB and a switch arrangement. This is nothing but the TPST switch which I have shown. Now this connection is anyhow done. Okay, up to this part anyhow connection is done. Our circuit connection only starts from output of the auto transformer. Okay, and I have already told you how to identify the output of the auto transformer. So if you look at this auto transformer, the down 3 terminals, these are the output terminals of the auto transformers. Okay, so input is already given, so this part of connection you need not do. Only the connection what we have to emphasize here is the connection from output of the auto transformer. Okay, from the output of the auto transformer. Now if we trace out the circuit in the circuit diagram, see here, first connection is from R, that is R terminal of auto transformer, you have to connect to the ammeter. Now I will just trace out that circuit connection. See here, this is the R terminal. Okay, see here, this R terminal is connected to the ammeter. So one terminal of ammeter we have to connect. So this is the connection. Okay, so next is, if you continue this path of connection, see here in the circuit diagram, now we have connected R to ammeter. Now ammeter to, from ammeter to RS. Okay, so you just see that this is the another terminal of our ammeter. This is the another terminal of ammeter, and this terminal we have connected to a terminal called as RS. Okay, anyhow, about this significance of RS, RE, then YS, YE, BS and BE already I have explained. Okay, so once again I'll just complete the circuit connection for the first part, whatever I have told. See here, from R to ammeter, ammeter to RS. This is the first connection. Okay, that is nothing but from R to ammeter, then from ammeter, that is the another wire, we have connected to RS. Okay, this is one connection. Next, second connection, it is very easy. You just look here in the circuit diagram. It says that Y is connected to YS, that is Y of auto transformer is connected to YS of load. Y of auto transformer is connected to YS of load. Okay, that is a very simple connection. You just see here that this is the Y terminal of auto transformer, and we have now connected to the YS terminal of load. This is the second connection. Okay, very simple. From Y terminal of auto transformer to the Y terminal of YS, to the YS terminal of load. This is the second connection. Okay. Now if you look in the circuit, what is the third connection is, third series connection is B to BS. That is B terminal of auto transformer to the BS terminal of load. Okay. So that is how is connected is, see, this is the connection we people are saying for B terminal of auto transformer. Now this B terminal of auto transformer, if you trace out, directly we have connected to the BS terminal of load. Okay, so this is the third connection. So remember that very simple connection we have done, that is R to ammeter, ammeter to RS, then Y to YS, B to BS. Okay, this is a very simple connection. Now, next part is we have to connect our voltmeters. So before we connect our voltmeters, as already has been explained to you, in the case of star connection, RE, YE, BE, we have to connect them. So we have to short them. Okay, we have to connect them. So we have to, before connection of voltmeter, you have to ensure that this RE, YE and BE are connected. Okay, so please now see here that this RE, YE, BE connection, how we have done. See here. So RE and YE are connected through a patch cord, and you can see that BE and YE, they are connected. That is, this is for the connection of RE and YE, they are short circuited, and another wire we have taken and we have connected to BE. That is, in order to short these three terminals, that is RE, YE, BE, practically we require only two wires, as you can see. Okay, in order to short the in order to short the three terminals RE, YE, BE, we require only two wires. Okay. Now the last part of this circuit is the connection of voltmeters. Okay, the last part of the circuit connection is the connection of voltmeters. Remember that all the connections whatever I have explained till now, so all the wires whichever I have used, so these all are thick wires. Everything is a series connection. But whenever you do the voltmeter connection for this one and this one, you have to use a thin wire. So we shall now try to know the connection for voltmeter. So for voltmeter, you see one terminal is here. Anyhow, Y you have connected to YS, right? So one terminal of voltmeter you can connect to YS or you can connect to Y. There is no change, because for parallel always we have two options. Remember that for parallel connection we always have two options. So that is one terminal of voltmeter you can either connect to Y or you can either connect to YS, right? So you can either connect to Y or YS, and the another terminal is you can just connect to the ammeter. So I'll just show you this connection first. See here, this is the voltmeter and this is what is the voltmeter which we have used for measurement of line voltage. See here how this has been connected. So this voltmeter, as already I have told you, one terminal we have to connect to YS and another terminal we have to connect to the ammeter, right? So that we can just verify here. See, one terminal it goes towards the ammeter and the another terminal it has been connected to YS. It has been connected to YS, as you can see. Okay, so this is the connection of one voltmeter, which is nothing but the voltmeter connected between the range of common and 600 volt, that which measures the line voltage. Now we have the last connection, that is the voltmeter connected between RS, because you see that already ammeter we have connected to RS, right? So the voltmeter we have to connect one terminal to the RS and another terminal to the path where we have shorted REYB. Anyhow we have connected REYB, right? So just remember that one terminal of voltmeter you have to connect to RS, another terminal is any one among this REYB. Okay, that we shall now verify. So this is the voltmeter. You see that one terminal we have connected to RS and another terminal of voltmeter, as you can see, this is the another terminal of voltmeter which we have connected to see RE. We have connected to RE. Okay, so this is the last part of connection. Okay, now we have to, before turn on the circuit, we have to consider certain precautions. So what are these precautions is, see here, first one is supply switch should be in off position. Okay, so before you turn on the circuit, before we energize the circuit, you have to ensure that this is in off condition. Okay, so this is in off condition means these lamps will be off. That is the first precaution. So second precaution is three-phase auto transformer should be in zero position. So please ensure that this knob is at zero position. Okay, this knob is at zero position. You have to ensure this. So this is the second precaution. Third precaution is make the tight connections. So whenever you do any of the connections, you have to ensure that these connections must be tight. So tight is nothing but, if I just try to see the connection should not come out. It should be tightly done. Okay, and you also have to ensure that initially all the switches in the resistive load should be off condition. Okay, so these are the precautions we have to consider before we energize the circuit. Start. Once you ensure that connection is done and the connection is tight and all the precautions have been carefully followed, you have to switch on this TPST. So whenever you switch on TPST, you see that the lights are on. It indicates that the circuit is in on condition. Okay, and you have to verify that whenever you switch on this, auto transformer is in zero condition, zero position, and all the meters should be in zero condition. So initially you please observe that all the meters should be in 0 condition. Okay, this gives you idea that your connection, everything whatever you have done is correct. Next is you have to apply 400 volts. So how you have to apply 400 volts is you have to monitor this voltmeter which is connected between 0 to 600. You have to monitor this voltage from this particular voltmeter. But how to apply the voltage is you have to slowly rotate the knob. Okay, you have to slowly rotate the knob given at the auto transformer. So what happens is once I start to rotate the knob of this auto transformer, voltage will gradually increase. So you can see here that I am now applying the voltage by rotating the knob of the auto transformer, that is the rotary switch, and you can observe here that this voltmeter gradually increases. Okay, you have to apply the voltage of 400 volts. So how to read the voltmeter I will explain you now. So whenever you apply the voltage, you see that the connections whatever has been done, okay, whatever the connections has been done, see here you have done the connections for common and 600. Mean to say that you have to read the upper scale. See here upper scale is 0 to 600. Okay, so it is how I am selecting that I have to read the upper scale is, it is because connection is done for common and 600. Similarly, if you do connections for 0 to 300, that is common and 300, you have to read the middle scale. And if it is for 150 volts, if you do the connections for 150 volts, then you have to read the bottom scale. Okay, now I am done the connections for 400 volts and I am reading the upper scale. Now this is what is the line voltage applied. So still now also you observe that the remaining 2 meters are showing us 0. Okay, remaining 2 meters they are showing 0 reading because load has not yet been applied. Now what you have to do is you have to turn 2 switches on. Okay, we have to apply this load by turning 2 switches on. So whenever we switch on 2 loads, you observe that ammeter will give you some deflection and the voltmeter which is connected to measure phase voltage will also give some deflection. Okay, now if you observe all the 3 meters, there is some deflection. Okay, so this is the stage, this is the stage where we have to take down the reading. Okay, now serial number 1. So VL is what I have applied voltage of 400. Okay, so wherever practical is there, you have to just note down the reading and see here IL is equal to IPH. You see the ammeter, it is 2 amperes, right? So it is giving you 2 amperes. I have written it as 2 amperes. Then VPH practical we have to note down. See, if you just look at the connections, already you know that the connections have been done for common and 300, right? So since the connection has been done for common and 300, so I have to read the bottom scale. So that now voltage is 232. So voltage is now 232 volts. So that I will write down the voltage as 232 volts. Okay, so this theoretical calculations you have to do at the end. Similarly, what you have to do is you have to take another 2 readings. Okay, the only thing what you have to do is you have to just apply the load. Okay, you have to increase the current by applying the load and you have to note down the current and voltage. So now it is 3.9 and this is 400. You can just see it is 400. It will not very much, will not be much more variation. So I think it is 398. So it's almost equal to 400 and this has now dropped to 230. Okay, that's what you have to note down. Okay, once the reading is over, okay, similarly you can also take the third reading. Okay, once the reading is over, you have to gradually switch off the load. So once you switch off the load, you observe that again ammeter is giving you 0 and V phase is giving you 0, only VL, which is the applied voltage, will be there. Now we have conducted our experiment, but still circuit is under energized condition, so we have to now switch off. So before we switch off, you have to ensure that you rotate this auto transformer knob back to 0 position. Okay, you have to rotate this auto transformer back to 0 position. So whenever we rotate this auto transformer back to 0 position, you see that this VL will also gets to 0. So that is the initial condition, right? So initial condition as it was there earlier. So now all the meters are 0. So once all the meters are 0 and load is also turned off, and this knob of auto transformer is again at the 0 position, we can turn off this TPST switch. This is the procedure for conduction of star connected load. Now we shall also discuss about the delta connection of the load. Okay, so this is called as the delta connection of load. Now up to this part, as you can see here, only the delta part is the change. Otherwise, whatever is now visible in the circuit, it is the same part of the circuit as applicable for our star connection. Only the change is with respect to the delta connection. So how this delta connection is done at the load, we shall now see. See, end is connected to starting. That is what you have to remember. See here, RE is connected to YS. Please remember, see here that RE is connected to YS. Similarly, YE is connected to BS. Okay, please remember that it is just end is connected to starting. End is connected to starting. Now, this BE and RS, okay, we connect them through the ammeter. Okay, please see that RS and BE, we connect them through the ammeter. Okay, which measures the phase current. Okay, that is the only difference. Okay, so rest of the circuit, it remains same. Only the change is with respect to the delta connection, and in the delta connection you see that, as already I have told you, RE and YS, they are connected. I have explained that. Then YE and BS, they are connected. There is a short circuit among them. Then RS and BE, they are connected through the ammeter. Okay, that is the connection part of our particular connection called as the delta connection. Now anyhow, we have to ensure that the previous precautions whatever have been discussed, that is load should be in off condition, and all the meters should not reflect anything. This auto transformer should be at 0 position and supply should be off. Next is we have to turn on the supply and we have to apply the voltage of 400 volts. That is the same procedure as we have followed earlier. So once you turn off the supply, you have to turn on the supply. See that these indicators are on, which gives you the idea that power supply is on. Okay. Now initially see that all these meters are 0, they are at 0 position. Now I have to rotate the rotating switch or the knob available at the auto transformer, and I have to apply the rated voltage. So whenever I rotate this, please observe that voltmeter gives you the reading. So I have to apply voltage of around 400 volts. Okay, so please apply the voltage around 400 volts. That's what you have to consider. So once 400 volts is applied, so we have to write that in our tabular column as 400 volts. And now you see that in the case of this delta connection, we have to now apply the load. So we have just turn on one switch. So whenever you turn on one switch, so if you just look at the circuit diagram, this ammeter is called as which reads the line current. Okay, this ammeter reads line current and this ammeter reads phase current. Okay, so in the column write down wherever IL practical is there, note down the ammeter reading, okay, which is now around 2.8 amperes, which is 2.8 amperes. So IPH, so you just add another column called as IPH practical. Okay, so in the column IPH practical, you also note down the reading of phase current, how much it is. Okay, so which is 1 ampere, which is 1 ampere. Okay, so in the case of delta connection, since line current is root 3 times of phase current, you can easily identify that the ammeter which gives you the larger reading is always measuring the line current, and the ammeter which gives you the less current is nothing but it is a quantity called as phase current, because for delta connection we know that IL is equal to root 3 I phase. Similarly, you can just turn on one more switch and see that the current is how much? It is around 5.8 amperes. So voltage remains same. Current is 5.8 amperes. So for this 5.8 amperes of current, look at the voltage, how much it is. So voltage is
3.2.
so look at the ammeter.
3.2.
So it is 3.2. So it is 3.2 amperes. Okay. So you can just load this switch. So the entire arrangement you can just put the load so that the maximum current should not exceed 8 amperes. So within that you can just take the reading. So now I am getting the current as 8.5 amperes. Okay, this is okay. Please, whenever you are conducting the experiment, please ensure that current is not beyond 9 amperes. Okay, so again the voltage is 400 volts, current is 9 ampere, that is the line current. 8.5 amperes, sorry, the line current is 8.5 amperes, and the phase current is 4.9 amperes. Okay, also ensure that this voltage is 400 volts in all the readings. Okay, so this is the procedure for conduction of delta connected load. Okay, so the procedure to turn off the circuit is, first of all you have to turn off the loads, and you have to ensure that the ammeter is giving you 0 reading, and you have to now make this voltmeter to bring back to 0 position. That you can do by rotating this switch back to the 0 position. Okay, that's what you can do. You can just rotate this. So whenever you rotate this, you can observe that the voltmeter comes to the 0 position. Okay, so this is the procedure to turn off.
Now we shall discuss the calculation part for this experiment. So here we shall discuss the calculations for star connection and delta connection separately. So these are the formulas which we have to use for the calculation, and you can see that whatever the readings we have recorded during the experiment conduction stage have been written over here. So these are nothing but the values from our experiment. Okay, so these are the practical values. Now, if you see in the tabular column, we have to calculate V phase theoretical. Okay, V phase theoretical, that is the phase voltage theoretical. So if you see this formula, then we can calculate that V phase is equal to VL by root 3. Okay, so this formula I have used, and we can calculate by substituting VL is equal to 400 volts. Okay, so if we substitute these values, then we shall get the answer as 230.94, which is nothing but 400 divided by root 3. So similarly here also you will get 230.94, and here also you will get 230.94. Okay, this is how you have to complete this column representing phase voltage. Similarly, you have to calculate power. So expression for power is given over here, that is root 3 VL IL cos phi. So you have to use this formula, that is power P is equal to root 3 VL IL cos phi. Now in the tabular column, as you can see, VL is available to us and IL is also available to us. Now this cos phi we have to substitute. Since already we know that we are considering resistive load. So we are considering resistive load, right? So in the case of resistive load, if we draw the phasor diagram, voltage and current will be in phase. Voltage and current will be in phase. Because of this, the phase difference between voltage and current will be zero. Right. So because of this, what happens in the cos of 0, it will be equal to 1. That is, power factor will become unity for the resistive load. So in the calculation, wherever this cos phi is mentioned, we have to substitute cos phi is equal to 1. In the calculation, we have to substitute cos phi is equal to 1, means it is unity power factor and it is for the resistive load. So based on this, if we substitute the values in the formula given over here, that is P is equal to root 3 VL IL cos phi, we shall get the power as, for this case, we shall get it as 692.82. And here for the second case, we shall get it as 2701.99. And for the third case, it is 2909.84. Okay, so this is the calculation part. Now here, what we have to observe is, if we observe the theoretical values and the practical values, they are almost equal. You can see here, right? So they are almost equal. So that is what is the one interpretation from this experiment, that is for star connection. And another thing is, this third column, that is V phase values, whatever we have written, this is as per this formula, right? Mean to say that VL is equal to root 3 V phase, it holds good for star connection. Okay, that information we shall get from the third column of this particular table. Okay, that is proved here. So next we shall move and discuss about the calculation part for delta connection. So for delta connection, again, the readings which have been recorded during the experiment stage have been written over here for the sake of convenience, so that we can just use these values and substitute and get the remaining values. Now if you look at the calculation, what we have to do is IL theoretical, that is line current, the theoretical calculations. Okay, so theoretical means we have to use the formula. That is what always we have to understand. So now we have to use this formula, that is IL is equal to root 3 I phase. We have to use this formula, and I phase is already available to us. That is, this column is available. Right now, all the values in this column must be multiplied with root 3. So that you shall get values as 2.73. We'll get the values as 2.73 and 5.54 and 8.48. Okay, so this is the calculation of IL theoretical values. Now similarly, we have to use the expression for power, which is root 3 VL IL cos phi. As already I have told you, cos phi we have to consider it is equal to 1. That is nothing but because of the resistive load. So because of the resistive load, power factor will be equal to 1, which is also called as unity power factor. Now for this, if we do the calculation, then we shall get the values as 1939.8 for first reading, then 4018.35 for the second reading, and 5888.97 for the third reading. Okay, so the calculations in the last part, that is P, the last column of this table, have been obtained. So these calculations have been obtained by using the formula, that is P is equal to root 3 VL IL cos phi. So whereas VL stands for the first column, IL stands for this column, right? So cos phi is equal to 1. Okay, so that's what have been tabulated. Now again, if you look at the comparison for theoretical and practical values, this line current, if we try to compare the theoretical and practical values, see, there is, so these values are almost matching. So again, see here, this value, right? So there could be some difference, right? So due to the ideal situation and the practical situation, but we can see that again these values are matching. And since these values are matching, and the values whatever I have calculated here, that is IL is basically by using this formula, that is IL is equal to root 3 I phase. Mean to say that for delta connection, this relationship holds good, that is IL is equal to root 3 I phase. This relationship holds good. Now, once we are able to conduct the experiment, we can just write down in result. You can just write down for any one of the row what is the value. That is, let us say that for star connection, VL is equal to 400 volts. Then V phase, so this theoretical value is equal to 230.94, and this relationship holds good, that is VL is equal to root 3 V phase. This holds good, and also line current is equal to phase current. Okay, so this what is, you can just write down for this experiment. So that is around 4.2 amperes. 4.2 amperes. Okay, so this is one part of our result. And for delta connection, again VL is equal to 400 volts, which is equal to V phase, and IL is equal to, we have calculated here, right? IL value, that is 8.48 amperes, 8.48 amperes, and I phase is 4.9 amperes, 4.9 amperes, and again this relationship holds good here, that is IL is equal to root 3 I phase. Okay, this relationship holds good. So wherever these values are there, always we have to mention the units, that is this is volts and so on, right? Now finally what we can conclude from this experiment is we can measure this line and phase values for current and voltage, okay, of given star and delta connection have been calculated. Okay, so next is theoretical versus practical values have been verified, and it's also proved from this experiment that it is also proved that for star connection VL is equal to root 3 V phase and IL equal to I phase. So also it is proved from this experiment that from delta connection VL equal to V phase and IL equal to 2, 3 degrees. Okay, so these are the important conclusions from conducting this experiment. Thank you all.